Hey math students, specifically geometry students. I'm going to talk about the converse of the Pythagorean theorem. I'm taking it from this book here, Geometry by Jurgensen. And if you got it, well, you're stoked. And if not, I'll have a link in the description. But that won't matter much because this is a very standard topic. And if you remember from the last lecture, and if you don't, I'll have a link to that. We talked about the Pythagorean theorem, just straight up. That's what this is. A squared plus b squared equals c squared. Where a and b, and this only happens in right triangles, where a and b are the legs and the c is the hypotenuse, it's always opposite the right angle. And the converse this, so, the straight up is if you square a and you square b, then that ends up being c. And this works in right triangles. Thus, if it worked, you have a right triangle. And the converse of that is you have a right triangle if this works. Back and forth. So what we see also in this section is the Pythagorean triples. And that's what these are. These are Pythagorean triples, 3, 4, 5, 5, 12, 13, and 8, 15, 17. These are the most common ones. And they're triples because 3, 4, 5 works in the Pythagorean theorem. If you have 3, I'll substitute that. 3 for A, 4 for B, 5 for C. So if you have 3 squared plus 4 squared, that ends up being 5 squared. That's 9, because 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, and 9 plus 16 is 25. That is a true statement. So the same thing, and you're going to have to take my word for it. See, really, if you just double the 3, that's 6, double the 4, and double the 5. If you triple the 3 and triple the 4 and triple the 5, if you scale it by 4, you get 12, 16, 20 if you scale these by 5. And any multiples of 3, 4, 5 work, that'll make a right triangle. And how do we use this? Well, it's almost like a cheat code. Because if I see I have a right triangle here, or the one that I had from before. And if this is a right triangle, and if I know that this is 12 and this is 13, then what is the value of this other leg right here? Well, that's part of the 5, 12, 13 triangle. So we know, if we know our triples, we just know, oh, it's 5. Done. I don't even have to do the Pythagorean theorem. Not that it's all that much work, but if you happen to recognize those, you're golden. So now we're led into these 3 useful theorems. And it's a lot of stuff here, but it's not that hard. This one says that if c squared is equal to a squared plus b squared. So essentially, if the hypotenuse is equal to a squared plus b squared, so the Pythagorean theorem's working, then it's a right triangle. Okay, that's obvious here. This one's pretty good here. If c squared is less than a squared plus b squared. So if you square these and it's, if this is less than a squared plus b squared, then what you have is an acute triangle. And this kind of makes sense. So this has to be smaller than these. So I'm not even looking at the squared just to make sense of this for me. If I have this right triangle, or if I have a triangle, and not a right triangle, and here's C, here's A, and here's B, and if C is less than A plus B, right? And I know that it has to be squared and all that, but I take those out. Just looking at this here, that means that this opening has to be small because these sides have to cave in. So if this is small, then this is a small angle, and that makes it an acute triangle. On the other side, if C is bigger, so if this is bigger than a squared plus b squared, as it says here, then as this is big, then this opening is big, and it's an obtuse triangle. So that's how I rationalize this, and we'll look at some questions here to make sense of this. So we got a few questions here, and I'll just do a few of them. Obviously, one would be kind of nice to start with. And we have, a squared plus b squared And then we're trying to figure out how does it relate to c squared. And a and b are going to be the shorter sides. So that's going to be 11 squared plus 11 squared. And we have to figure out how does that compare to 15 squared? Well, that's 121 plus 121, and this is 225. And so 121 plus 121, that's 242. So this is squeezing this in, 242, and that's greater than 225. So what that tells us is that has to be, an obtuse triangle. Oh, and we have to be careful too. What kind of, is it acute, right, or obtuse? And on one of these, you can't even make it a triangle. I'll have to think about which one that is. See, you know it can't be a triangle if the sum of the two smaller ones is smaller than the longest side. And I don't see one here that necessarily does that. So maybe they all possibly could be triangles. Okay, let me grab another one. Like, how about number 3? Number 3, that is 8 squared. I'm going to square them all. Plus 8 rad 3, and that has to be squared. And how does that compare to 16 squared? So 8 squared is 64. 8 rad 3, that's 8 squared. So plus, this is 8 squared, and this is the square root of 3 squared. So that would be 64 plus 64 times the square root of 3 squared is 3. And how does that compare? Well, I forgot what 16 times 16 is. That's 36. That's 9, 16, 6, 5, 256. Okay. So how does that compare to 256? Boy, this is going to be kind of close, huh? So we have 64 times 3. 64 times 3, can't think of that right now. 12, 18, 19, 192 plus 64. That is 6, 5, 2. Oh, look at that. That's 256 right there. And that's equal to 256 here. So this is a right triangle. Let's look at, let's see. Oh, number 8. Number 8's great. I like that. 8a, you have 33 squared plus 44 squared. And how does that compare to 55 squared? Well, if you remember those Pythagorean triples, remember one of them was a 3, 4, 5. Well, if you can multiply these by 11, and you would have 33, 44, 55, and this is a right triangle. And I don't even have to check it. I know that 33 squared plus 44 squared is equal to 55 squared. All right, so we got a few others here. I'll jump into number 12. And in number 12, AC is 10. AC is 10. BC is 17. And CD is 8. This is 8. The question is, decide if triangle ABC is acute, right, or obtuse. So ABC, okay. That means that I have to use the Pythagorean theorem a couple times to figure out this length and this length. And then I have to use the Pythagorean so I have to use the Pythagorean theorem 3 times. One time to find this length, one time to find this length, and then a third time to compare these 3 lengths. So I also could use similar triangles, but I'm not going to do that. So for the triangle ACD, that would be 10 squared is the hypotenuse, is equal to 8 squared plus, I don't know, x squared. I'm calling this x right here, x squared. So that would be 100 is equal to 64 plus x squared, subtract 64. And you have 36 is equal to x squared. If we take the square root of both sides, we have x is equal to 6. So this is going to be 6. Oh my God, I already know that look at this. If I have triangle CDB, well, duh. If this is 8 and this is 17, that's an 8, 15, 17. It's one of the triples that I was showing you earlier. So 8, 15, 17, that means that if I call this y, that's 15. If you did the Pythagorean theorem, you would know that it is that. So that's 15. So the total x plus y is going to be 6 plus 15, which is 21. So I'm going to erase some stuff here so I can clean this up. And so I know that I'm going to erase more stuff here. So first, this is 10, this is 17, and this is 21. And I'm wondering, no, that's not a triple, 10, 20, 10, 17, 21. So I don't recognize that as a Pythagorean triple. So what I would do is I would just use a Pythagorean theorem. Is 10 squared plus 17 squared equal to 21 squared? That's 100, obviously. I know that 17 squared is 289. And 21 times 21? Oh, God, I can't remember. It's 400 something. 21 times 21 is 1, 2, 2, 4, 441. Okay. So that's 441. And let's see. I don't think this is going to work because 289 plus 100 is 389, which is not equal to 441. Okay. So it's not a right triangle. So we know it's not right. And c squared is bigger than a squared plus b squared. So that means that this would have to be obtuse. And what did I do? So number 12. Number 12 is obtuse. I should redo this little part so that shows that. Remember, this would be a squared plus b squared is equal to c squared. I said it equal, but it's not equal. In fact, it's bigger. So this is the statement on number 19. We have these two triangles here, which will be used for part B, but part A is complete the statement in Theorem 8.5. If the square of the longest side of a triangle, here it is greater than the sum of the squares of the other two sides, then the triangle is an obtuse triangle. And this is the one that says if c squared is greater than a squared plus b squared. That's essentially what it's talking about. But let's get into that proof. So I moved this up a little bit, and we're asked to we're given that triangle RST. So RST right here, and L squared, okay, is greater than j squared plus k squared. Is greater than j squared. So this is an obtuse triangle because that's by that theorem. And so prove that RST is an obtuse triangle. So we know, and we're going to use the theorems to prove it. And we're going to go with that hint. The hint says, start by drawing the right triangle, UVW, with legs J and K. So I drew it. And we have that diagram here. And what we're going to do is we're going to compare lengths from this triangle to this triangle. And if this is a right triangle, then we can compare. And we'll simply say that n squared is equal to j squared plus k squared, talking about this, because it's a right triangle, and we can follow the Pythagorean theorem with that. Now I need to point out a critical step here also, that this j is the same length as that j, and this k is the same length as that k, but the L and the N are not the same. So L squared is greater than, okay, that's given. N is equal to that, okay, so if L squared is greater than this sum, and N squared is equal to this sum, that means that L squared is greater than N squared, because we're substituting. Instead of writing j squared plus k squared right here, we're writing N. N's getting substituted for that sum. So that means L squared is greater than N squared. And if we take the square root of both of these, L is going to be greater than N as well. So that sets us up for the next step here. So the measure of angle S is bigger than the measure of angle V, and V is exactly 90. We do know that. So, and what can we state? The side inequality theorem, which states if you have two sides here, so JK is the same thing, so they are obviously the same. If the third side is different than the third side of the other, so if the third side is bigger than the third side of the other one, of the second one, then the angle S, angle opposite that side, is bigger than the angle opposite of the second one. So there we are saying that angle S is definitely greater than 90. And so then that allows us to say that I'll squeeze in number 6. So triangle RST is an obtuse triangle. Obtuse, and then hopefully you can just allow me to not write the word triangle. And the reason is really just the definition of an obtuse triangle. Triangle. And there you go. So I'm hoping the review of all these have helped you. Let me know in the comments if you have any further questions or any requests. I take requests. Hey, how about that? All right, take care.